Sarvesham Shubhodayah. Namaste. We welcome you all to this program jointly organized by Sant Rajinder Singh Ji Maharaj Chair, IIT Madras, and Samskrita Samiti, an independent student body at the Institute. On behalf of all, I extend a warm welcome to Professor Amba Kulkarni, the chief guest of today's event. Now I request Professor K.S. Kannan from HSS Department to introduce our guest to the audience.
Sarvebhyaha namaskaraha. Sant Rajinder Singh Ji Maharaj Chair etat pitham evancha atra Samskrita Samitihi iti ubhayoः आश्रये अयं कार्यक्रमः प्रचलति. अस्मिन् दिने प्राचार्या अम्बा कुलकर्णी महोदया संस्कृतछन्दश्शास्त्रे गणितीयाः प्रक्रियाः यादृश्याः भवन्ति इति तं विषयम् अधिकृत्य प्रवचनं करिष्यति. आदौ तस्याः स्वागतं कर्तुं मम महान् सन्तोषः. Professor Amba Kulkarni is a computational linguist. Since 1991, she has been engaged in showing the relevance of Indian grammatical tradition to the field of computational linguistics. She has contributed towards the building of anusargs, language accessors, among English and Indian languages. She is the founder head of the Department of Sanskrit Studies, University of Hyderabad, established in 2006. Since then, her focus of research is on the use of Indian grammatical theories for computational processing of Sanskrit texts. Under her leadership, a consortium of institutes developed several computational tools for Sanskrit, and also a prototype of Sanskrit Hindi machine translation system was developed. In 2015, she was awarded a Vishishta Samskrita Sevavrati Sammana by the Rashtriya Sanskrit Samsthan, New Delhi, for her contribution to the studies and research on Sanskrit-based knowledge system. She was a fellow at the Indian Institute of Advanced Study, Shimla, from 2015 to 2017. Her biodata runs to more than a dozen pages. I have only given a very brief picture to add just a few more points to her work so far. She is right now the professor and head of the Department of Sanskrit Studies, as I said earlier, in the University of Hyderabad. You must all make it a point to visit Samsadhani, a website, so in which her remarkable achievement of showing the wealth of Sanskrit vocabulary, so as derived from the roots, so is so very well displayed and so easily accessible, and makes the vocabulary of Sanskrit very transparent. So it was Sir William Jones who said that when they discovered Sanskrit, so to say, so he said that Sanskrit is a language which is more perfect than Greek, more copious than Latin, and more perfectly structured than either. So this copiousness of the vocabulary of Sanskrit and how words derived from roots, so there are just 2000 roots in Sanskrit, and how vast repertoire of vocabulary in Sanskrit, so both poetic and scientific vocabulary are derived from the roots in a very systematic way, in which comparable to which there is no other language and no other grammar in the world. So is very beautifully shown by that Samsadhani, which you must all indeed visit. She has continuously shown the relevance of Indian traditional shastras in modern context. See, it has been the fashion of many Sanskrit professors and teachers to praise Sanskrit, so and say that it is very useful even to this day and so on. But she is one person who has continuously shown the relevance of shastras to modern studies in a manner that scientists themselves would easily and readily and heartily agree. So it is so very convincing because it is full of very clear demonstrations. She has also shown Pawnimi as the foremost information scientist. There has been much talk about Sanskrit being the best computer language. What exactly it means and what it does not mean has been very clearly demarcated by her and established by her. She has delivered keynote addresses in various conferences and universities. The list is too big, and therefore I am only summarizing in 2 pages in one line. She has guided some 12 students for her PhD, for their PhD, and 4 more are doing PhD under her, and 6 students have done their MPhil under her. She is a member of various academic bodies, and she is also, for example, she is a member of National Sanskrit Council. She has been a reviewer for various journals, Indian and abroad, and she is a resource person for various organizations and various conferences. She has organized workshops and symposia on Sanskrit computational linguistics. She has been a partaker of, undertaker of many projects and collaborations, and she has edited or authored nearly 10 books, and especially international proceedings on Sanskrit computational linguistics. A recent book published by her, so that is published by Indian Institute of Advanced Studies and DK Printing Publishers. So DK Print World is a book called Sanskrit Parsing, which gives the distilled wisdom of ages of grammatical and other discussions in Sanskrit. Let me not take much of your time. I request now Professor Amba Kulkarni to please proceed with the talk.
Thank you, sir, for nice introduction. I do not know if I deserve all these good words. One point I would like to mention here, which I think you missed, and that is, I am basically a student of mathematics, and that is how this mathematics title is there. Otherwise, of course, for last more than 30 years, I have been working in the area of computational linguistics, but my basic training is in mathematics. So even in computational linguistics, I look at the linguistics, trying to model it from mathematical point of view. And this is, of course, well, there are many here like Professor M.D. Srinivas and M.S. Sriram, who have been working in the area of mathematics, Indian mathematics, and there are many talks by both of them on these topics. So what new I am going to talk on today? There is one point which I would like to emphasize on, and that is the recursion, the concept of recursion in Pingala's Chandas-śāstra vis-a-vis the same algorithms which Pingala has given recursively, the same were given by Kedarnath Bhatt later in the 10th century in iterative manner. So this is the point which I would be emphasizing. Otherwise, some of you might have heard his talks, so you may not find anything new, but this is one point which I will be bringing in. Okay. How many of you have mathematics background, or who do not have mathematics background, maybe? Okay. So I think I can skip some of these slides then. I thought there will be some Sanskrit scholars who may not have mathematics background, so I had some of these slides. Well, anyway, recursion, we know it occurs when a thing is defined in terms of itself. And we have these examples of factorial Fibonacci or fractals. Even Khajuraho temples. See, Khajuraho temples, all of us know that they, or I should say, they are wrongly projected as just the temples where the Kama-shastra pictures are there, the sculptures are there. But look at this picture where it's all recursive structure which is here, and nobody tells us about these things. To understand recursion, you must understand recursion. So there is one AI scientist, Douglas Hofstadter. He has written a book, I Am a Strange Loop. This has, of course, it has to do with Gödel's theorem and then also the self. It's little philosophical, but then using that I will say, if you already know what recursion is, well, you know, just remember the answer. Otherwise, find someone who is standing close to this person, because he says I am a strange loop, and then ask him or her what recursion is. So this continues. So basically in recursion we try to reduce a problem with similar problem with smaller size, and the base case is trivial one, as in the case of Tower of Hanoi. All of you know the story of Tower of Hanoi. There is a story related to what is Brahma's day, and they say, well, there are 3 pegs, in one peg there are 64 discs, one above the other. You transfer all these 64 discs to the other peg with one constraint, that the smaller disc should not be below the larger one. With this constraint you have to transfer this, and whatever time is needed to transfer these 64 discs is the day of Brahma. Okay. So now to transfer these, suppose I know how to transfer 8 discs from one peg to the other. I know how to transfer 9 discs, because first I will transfer 8, then the 9th one I will transfer, and again I will put back the 8th one. So there is a recursion involved. The natural solution for this is recursive, and the trivial base solution is, the base condition is, when you have only one disk, you just transfer it. That's it. In my talk there is another term, combinatorics, which is a branch of mathematics which deals with combinations of objects belonging to a finite set under certain conditions, which satisfy certain conditions. And the third word in my talk is Chandas-śāstra. Now Chandas-śāstra, as all of us know, many of us know, is basically a science of meters, and this was developed, it came into, this was developed by Pingala, and the reason for this was to study the Vedas. The Vedas they wanted Vedas to be protected, and in order to protect Vedas, because Vedas are written in various chandas, you should know the chandas so that you can protect them. So Pingala describes various chandas, but then he does not stop there. He goes one step further, as we have observed in various texts in Indian Shastras. Prayojanam vina na mandopi pravartate. There is some prayojana for each of these Shastras, but they do not stop when the prayojana is satisfied. They go one step further and try to abstract out the things. So this is what Pingala also has done. Pingala has tried to abstract the mathematics behind all these chandas. The Chandas-śāstra, it has 8 chapters, and all these chapters, they are in the form of sutras. So he has given the text in the form of sutras, and sutras, as all of us know, alpaksharam asandigdham saravat vishvato mukham astobham anavadyam cha sutravido viduhu. Sutram sutravido viduhu. So alpaksharam, it has minimum number of words. Asandigdham, it is unambiguous. Saravat, it is general. It contains the essence. Vishvato mukham, it has universal validity. Astobham, it does not have any unmeaningful words. And anavadyam, it does not have any faults, devoid of any fault. So it is something like a mathematical formula, where in mathematical formula each of the letters in the formula, each of the symbol in the formula is important, meaningful. Same is the case with the sutras also. Now this Pingala Chandas-śāstra, the last chapter, has some 35 sutras, and from 820 to 835, the last 16 sutras, they deal with algorithms related to combinatorial mathematics. So what are these? Well, these sutras, they describe various things. There is a spelling mistake, just ignore following. So prastaraha, nashtam, uddishtam, again u should be short, ekadvi adi laga kriya, sankhya and adva yoga. These are different operations which Pingala is describing. What is prastara? Prastara is to get all possible combinations of laghu and guru. Then nashtam is to recover the lost or missing row in the prastara, which can be considered to be equivalent to getting a binary equivalent of a decimal number. Uddishtam is the reverse process of it, to get the row index of a given row in the prastara, which is equivalent to getting decimal value of a binary number. And then there are ekadvi adi laga kriya, which is equivalent to computing NCR, and sankhya or sankhyana they call sometimes, it's computation of 2 raised to n, and there is adva yoga, which computes total combinations of chandas ranging from 1 syllable to n syllables. So let us start with the prastara. There are 4 sutras in the Pingala Chandas-śāstra: Dviko Glau, Mishraucha, Pruthagla Mishraha. I have split the words purposely because I wanted to tell you what the meaning of each of these is, and Vasavastrika. So this Dviko Glau, Dvik is 2. So Dviko Glau is Ga and La in Dvivachana, so Glau. So he says there are 2 types of one akshara, namely Ga and La. And if I replace Ga with 0 and La with 1, I have 2 rows, 0. I have here 2 rows, one is 0 and the other one is 1. Mishraucha. So Mishra, you can mix them. Pruthagla amishraha, Pruthak is separately, and amishraha, so you are keeping them 2 separately, and then to them you mix Ga and La separately. So what he is saying is, well, sometimes this this sutra is taken as an explanation for getting the syllable combinations of 3 Ga and Las, but I am taking them together because if you say Mishraucha, you can mix them. In which way to mix them, that is not clear. And therefore, this Pruthagla I am taking with this, and Amishraha. So first you have this GL, here also you had GL. These are Amishra, so keep them separate, and then separately mix them with Ga and La. So now you get, I have also written here, replace G by 0 and L by 1. So you have 0, 0, 1, 0, 0, 1, 1, 1. But this is not the order we write binary number expansion. What we have actually is the mirror image of this. Instead of 1, 0, we should have 0, 1. Instead of 0, 1, we should have 1, 0. So here they were writing from left to right, whereas when we write the numbers, we write from left to right to left. Okay. So here you will see this difference. Another difference you will notice, the counting started with 1. So you had 1, 2, 3, 4, whereas in binary number system we count starting with 0. So this 0, 0, we say this is the 0th representation of decimal 0 in binary, or the representation of 1 in binary is 0 1, but here we will have the representation of 1 as g g and representation of 2 will be l g. So this slight difference is there between the Chandas-śāstra representation and the binary 2-bit representation that we are familiar with. Then you have the third sutra which says Vasavastrika. Now Vasavaha. What is Vasavaha? In the first chapter there is another sutra which says Ashtau Vasava iti. So those who know these stories, there are 8 Vasus, for them it is fine, but in the Chandas-śāstra, in the book itself, in the Chandas-śāstra itself, Pingala is mentioning this. In the first chapter he is giving all the definitions which he will be using later. So there he defines Ashtau Vasava. So there are 8 Vasus. So he says there are 8 triplets. Now how do you get these 8 triplets? Again, just by repeating the same process which was described earlier, that Mishraucha and Pruthagla Amishraha. So you are using the same method. So you have here this 2 by 2 matrix and add G, then here the expansion with 2 bits or 2 girlers and add L to it. And if you replace G's by 0, G and L's by 0 and 1 respectively, we get this. Take the mirror and we get the corresponding numbers in modern notation. Now what we see here is, what Pingala has done is he has given the base condition where to start. See, for recursion there are 2 things involved. One is the base condition, or when to terminate, where to terminate, and how to go from one step to the other. So he has given both these things. The base condition is given and transition from base condition to the next, that is mentioned. But he is not saying that repeat this. Now just imagine you are teaching a child, when you have told child how to get the matrix for 3 G and L's. Naturally from 2 to 3, if this transition is told to him, then he will naturally go from 3 to 4 automatically. So here the sutras that are given are not for dumb computers, but for intelligent human beings. And therefore he is not mentioning it that you repeat it to get the next one and so on. This is understood. Now let us come to what Kedar Bhatta has given. See, this was in 10th century. So a long period has elapsed, and this particular text must be there in the normal teaching curriculum. And you know that if you ask any mathematics teacher, teaching recursion is a bit difficult than iteration. So that might have been the reason that Kedar Bhatta had to switch over to iterative algorithm. And what is this algorithm? The step-by-step procedure he has mentioned. Pade sarva gurau adyat lagunyasya gurau adha yatha upari tatha shesham bhuya kuryat amum vidhim une dadyat guru neva yavat sarve laghu bhavet prastaraha ayam samakhyataha chando vichiti vedibhi. So what he is saying is, Pade sarva gurau adyat, in the beginning all are gurus. Laghu nyasya guroho adhaha. So now below the guru you write laghu. Then the first guru again you have to take. Adyat should also be repeated here. And then yatha upari tatha shesham, remaining things are to be copied as it is. Une dadyat gurun eva, suppose there are anything left, then you replace them, you write guru in place of them. Yavat sarve laghu bhavet, you repeat this till all become laghu, and this vidhi is called the prastara. So we start with all gurus, then below the first G, L is written and remaining things are copied as above. In the second, below the second G, this was the first G. So below this first G, L is written, this is copied as it is, and in the remaining part G is written. Again below first G, L is written, this is copied as it is. Below first G, L is written, and here these are filled with G's. Below first G, L is written, these are copied as they are. Again here below first G, L is written, this is copied, and here G is filled in. And now we get all else, we stop here. Okay, so you see that this was totally an iterative process. So here there is no transition how to go from a prastara of 2 syllables to 3 syllables, that is not mentioned. Directly he gives a method for getting the prastara for n syllables. Okay? Whereas in the previous only transition was mentioned. So now suppose you are asked to write a prastara for 5 following the pingalas, you have to start with 2, then 3, then 4 and then 5. Whereas with Kedar's algorithm, you can just start with 5 syllables and write the prastara for it. This is the difference between these two. Now there is another algorithm, this is for Nashtam. Now in earlier days they used to write this, it is called Patiganita, or they used to write on Sant. So because of some reason, suppose one row gets deleted, then how to recover it? Now in the case of Kedar's algorithm, if any one of them is deleted, you can always recover from the previous row because you know the algorithm. But that is not so in the case of Pingalas. So Pingala has given another method, Lardhe Saike Ga. This particular algorithm I remember when I was teaching in engineering college, the computer science students, conversion from decimal to binary and binary to decimal. And Malvino's book I used to follow, there some 8 or 10 steps were given. And then students had to remember all those things. Here you have just 2 simple sutras, so small, so succinct, and you remember the algorithm. And what is this algorithm? For conversion from binary to, it is decimal to binary, sorry. So Lardhe Sa Eke Ga. So what does it mean? La Ardhe. Ardhe. If you can have it, if you can divide it by 2, that is if the number is even, then write L, else add 1 and then half it and write G. Sa Eke. So add 1 and then write G. So here is a number 5. 5 is not divisible by 2, so we add 1, divide by 2 and we write G. Now this 3, now see here Pingala has never mentioned that you repeat this and where to stop, that also he has not mentioned, okay. But you have these 2 steps, so go on doing these steps one after another, repeatedly, not one after other, repeatedly. So you have 3 which is again odd, so add 1 to it, divide by 2, write another G. See, you are writing from left to right, okay. Whereas numbers we normally write from right to left, here we are writing from left to right. Then you get 2, 2 divided by 2 is 1, you write L. Now, how do I know that I have to stop here? Because this 1 is odd, so next will be 1 plus 1 by 2, same 1. So now you have reached a fixed point and therefore you have to stop. So it is not mentioned explicitly, but we understand it as a human being. When it is giving same number, there is no information in it, so we stop. Okay. So we have here GGL, which is 001. Take the mirror, you get 110. Well, now again you will say 110 is 6, it is not 5, but since we start counting from 1, we have this 5 is 110.
So what is only for a 3-syllable prastara? If it's a 4-syllable prastara, what do you do?
Right. So there then you will have to write one more L, depending on how many syllable prastaras are there. Yes. So if it is a 10-syllable prastara, you go on writing remaining. Fine. Agree. Now the Uddishtam. Uddishta is the reverse of Nashta. See, in Nashta, the row is totally deleted from the prastara and now you want to recover that row. So this was given a decimal, what is the corresponding binary equivalent. Uddishta is, suppose now you are given some binary, what is the corresponding index in the prastara. So what is the decimal equivalent of it? And here now he is giving these two rules. Pratiloma gunam dviladyam tatah gi ekam jahyat. So pratiloma gunam in the reverse way, in the reverse order. Dvihi la adyam. Dvihi multiply by 2. Starting from the first L. And then tatah, from that, gi, if the syllable is guru, ekam jahyat, subtract 1. Again here the initial condition is not mentioned. Okay. See, it says multiply by 2. Which number is to be multiplied by 2? Initially there should be some number, that he has not mentioned. But then when it is multiplication, we don't start with 0, we start with the identity element 1, which is the identity element for multiplication. So we have, suppose GLG is there, the first L we start with that, then multiply it by 2 and then continue with this result, write this 2 here, multiply it by 2 again and subtract 1, so you get 3. So for GLG we get 3, which is the, so this is the third row. If we want to see GLG, here you will see GLG is the third row in the prastara of 3. Now Kedar has given the algorithm for Uddishtam in a different way. Uddishtam dvigunan adyat upari ankan samalikhet. It should be upari ankan. Lagustha yetu tatra ankaha taisa ekaihi mishritaihi bhavet. So to get the row number corresponding to the given Laghu Guru combination, that is the Uddishtam. The Uddishta, what is Uddishta? Given a Laghu Guru combination, what is the row number? So to get the row number corresponding to the given Laghu Guru combination, starting from the first Adyat Samalikhet, right? What is to be written? Dvigunan, double of the previous one is assumed here. Upari, we have to write on the top of each Laghu Guru. Upari, we have to write these numbers on the Laghu Guru. Lagustha yetu tatra, whatever numbers are there on the Laghu, they are added sa ekai mishritaihi, all those numbers are added with 1 and that gives you the row number. So suppose GLL is given, we write 1, then double of 1 is 2, double of 2 is 4, and then whatever is there on top of L, we add them, and to this we add 1 and we get the row number. So for GLL we get 7 and we can verify this. GLL was the 7th row in this matrix. So you see here in the previous one, well, this the two algorithms, Pratiloma-gunam dvi-adyam and tatah ekam jahyat, you are repeating this process here. There is a loop, but the same process is repeated again and again with different initial condition. Whereas here, first you write down these numbers 1, 2, 4, etc. and you are adding them. So this is something which is a kind of iterative process, whereas the previous one was recursive. Sankhya, or sometimes it is also called Sankhyana. In some books I saw Sankhyana also. There are these 4 sutras, Dvi Ardhe Rupe Shunyam Dvi Shunye Tavat Ardhe Tadgunitam. And here we find this word Shunya for the first time as far as I know. But this Shunya is here just a placeholder. So what are these 4 sutras saying? Dvihi Ardhe. Ardhe, if it is divisible by 2, then write 2. Dvihi. Rupe Shunyam. Now Rupa is 1. It's again a mnemonic like Vasu, Vasavastrika. Vasu was Ashta. Similarly Rupa is 1. So Rupe Shunyam. If it is not divisible by 2, then subtract 1 and write Shunya. Dvihi Shunye. If the answer were Shunya in the previous one, then multiply by 2. And Tavat Ardhe Tadgunitam. If it were divisible by 2, then Tadgunitam you multiply with itself. So what is it saying? Suppose we have number 8, this is divisible by 2, so I have divided it by 2 and I have written 2. Again 4 is divisible by 2, I have written 2. 2 is divisible by 2, so I have written 1 here and 2. This 1 is not divisible, so I subtract 1 from it, I get 0 and I write 0 here. And now whatever is written here 0, 2, 2, 2, you start with them. If it is 0, multiply it by 2. So multiply which number by 2? Since initially nothing is given, we start with 1 again because it is a multiplication process. So we multiply 1 by 2, we get 2. Then Tavat Ardhe Tadgunitam. So if 2 means it was divisible by 2 and therefore we have written 2 here. So if 2 is there, then multiply 2 by 2, so square it, we get 4. Again there is 2, so square it, and again there is 2, square it, we get 256. So given 8 we are getting 256. What is it? We are getting 2 raised to n. Okay. And the importance of this algorithm, there are 2 interesting things which I found. One is the concept of stack. See, here he is going on writing these 2, 2, 2, 0 and he is keeping them as a stack and then removing one after another. This is something which is interesting. Another thing is, this is an efficient algorithm for finding power of 2. Yes.
You said it's 2 to the power of 8, but if it is 2 to the power of 7,
Huh.
then the very first step itself will be very different.
Yeah, sure,
If you
sure.
start with 8,
Sure,
then
sure,
you
sure.
come down, but
Yes,
you start
yes.
with 7 or 9.
Yeah. So fine. If it is an odd number, then the number of steps will be different. But the algorithm is this way: 2 raised to n. If n is even, then we can write it this way. If n is odd, take 2 out, and then for the remaining, you can again use this. Okay? And we start with 1. Okay? Okay. And this algorithm has the complexity of log n, and Donald Kruth has referred to this algorithm in his book, and he calls it a binary method. Of course, nowadays there are more powerful algorithms, but imagine in those days, around 2500 years back, he has given this algorithm where an important concept of stack was used, which was something really astonishing for me. The concept of stack is used, and the binary method is used, which gives you efficient way of calculating these numbers. Then you have Dvidvi unam tad antanam. This is the next sutra. Now what this sutra says? To get, this is the, it's called, the term is Adva Yoga, and Adva Yoga means yoga is the sum. So this gives the sum of all the chandas with number of syllables less than or equal to n. So to get the Adva Yoga, multiply the last one, Tat Antanam, by 2, and then subtract 2 from it. So what this is saying is, sigma I from I equal to 1 to n 2 raised to I is 2 raised to n into 2 minus 2. And then you have the Meru Prastara. These two sutras, Pare Purnam iti. Well, from Pare Purnam, what do we understand? There are two interpretations I came across. First interpretation says, to get the number of meters with the next number. See, here we had Adva Yoga, Dvidvi unam tadantanam. So we have up to n, we have added all the chandas that are possible with syllable 1, syllable 2 up to syllable n. Now how many will be there with syllable n plus 1? So it says Purnam. So you don't subtract 2 and you will get the number of syllables. This is one interpretation. Another interpretation I got from Halayuda's commentary, and I will not go through the commentary, I will directly explain what he is doing. Pare Purnam, first start with these ones. Pare means on the two sides you make it complete. Well, this interpretation is given in Halayuda, and also when I visited one Gurukula also, because I wanted to know traditionally how they are teaching this. And then the teacher, the Acharya there, he explained me the way I am explaining now. So you start with these ones. So first complete the pare, that is the two sides. Then complete the inner one. And how to complete this? Then here he is using the commentary from Rita Sanjeevani. Halayuda's commentary, that you add 1 and 1 you get 2, 1 and 2 you get 3, 1 and 3 you get 4 and so on. Then you complete the inner one and so on, and thus you get the complete Meru. So this is the process of completing the Meru. And what these numbers are, they are NCRs, NC0, NC1, etc. Kedar Bhatta has given the algorithm in a different way. Varnan Vrutta Bhavan Sa Ekan Uttaradhata. This I do not know, there is something wrong. It is Uttara and Adhataha Sthitan Ekadikramataha cha etan upari nikshipet upantyato nivartet tyajatna ekaikam urdhvataha upari adhyat guroh evam ekadvyadi lagakriya. So what he is saying is, whatever is the number of given syllables, write those many ones, uttara, that is from left to right, and adha from top to bottom. Then add the numbers in the previous row to its left occupant and continue this process leaving the last number. Continue this for the remaining rows. The last number in the first column stands for all gurus. The last number in the second column stands for one laghu, and so on. So suppose you have 6 syllables, you write 6 ones here and 6 ones here. Then you add this 1 plus 1 2, 1 plus 2 3, 1 plus 3 4 and so on, and go on reducing the number of rows. So here you will fill only these 5, then next only 4, 3, 2 and 1. This one is the total number of rows with all gurus, then with 1 laghu, with 2 laghus, with 3 laghus and so on. So we get NC0 and so on. Then another algorithm which Kedar Bhatta has given for Sankhya is Laga Kriyanka Sandohe Bhavet Sankhya Vimishrite Uddishtanka Samaharaha Sa Eko Va Janayet Imam. So there are 2 formulae he is mentioning here. Laga Kriyanka Sandohe Bhavet Sankhya Vimishrite. So by adding the numbers, all the numbers of Ekadvi Adi Laga Kriya, what is Ekadvi Adi Laga Kriya? Ekadvi, so Ek Laghu, Dvi Laghu, Tri Laghu, etc. So these are the numbers which we get from Ekadvi Adi Laga Kriya. So when you add all these numbers, you get the Sankhya. And another formula he gives, Uddishtanka Samaharaha Sa Eko Va Janayet Imam. So by Samahara is addition of all the numbers. Of what? Uddishta Anka. Uddishta was 1, 2, 4, we were writing the numbers twice the previous one. So all those numbers in the Uddishta Kriya, add all these and to it add 1 and you get the Sankhya. So Sankhya, as you remember, let me go to here, this was the Sankhya 2 raised to n, okay. And here Pingala had given the algorithm which is recursive in nature, whereas Kedar is giving another explanation for this, another formula for this, or rather he is giving 2 formulae. The first formula says, whatever are the numbers in Ekadvi Adi Laga Kriya, that is NC0, NC1, NC2, etc. So if you have 6 bits, 6 syllables, then 6C0, 6C1, 6C2, etc. Add all of them and you get 2 raised to 6. And the Uddishta numbers are the powers of 2. So this is like you have in our decimal system we have 1, 10, then hundreds place, thousands place, etc. In binary you will have 1, 2, 4, 8 and so on. So you have 1, 2, 4, 8, 16, 32. These are the 6 numbers. Add all of them and add 1 to it and you get 64. So these are actually, they correspond to these two formulae. 2 raised to n is sigma sigma from r varies from 0 to n NCR, and another formula 2 raised to n is sigma 2 raised to I, where I varies from 0 to n minus 1 plus 1. So you are getting, so basically Kedarnath was aware of these two well-known formulae. And now I am going to stop here with the last comment on the recursion in prosodic meters. Duration, we know Laghu is short duration and Guru is long, or 2 units, let us say 1 unit and 2 unit. Then if I denote Sn, if I use Sn to denote number of strings with duration n, how many strings with duration 1 will be there? L, only 1. We can have only L. But the possible combinations of strings with duration 2, it can be either LL or just G. So there are 2. What about 3? So if we want meter with duration 3 or string with duration 3, you have a string with duration 2 and add L to it, or a string with duration 1 and add G to it. So essentially this is S3 is S1 plus S2, and similarly S4 will be S3 plus S2, because S3 we add Laghu to it, we get 4 duration of 4, and to S2 if we add G we get duration of 4. So we have Sn, which is Sn minus 1 plus Sn minus 2. All of us know this as Fibonacci. But this was there in Virahanka in 7th century. Virahanka has noted this, and Hemachandra in 12th century. And in fact, Pingala's Pare Purnam also is taken as another explanation for this Fibonacci. So with this, now I stop. Thank you very much.
In fact, recently was the, I'm sorry, if there's some closing remarks, we will have the discussion.
Yes.
Thank you, madam. Now the floor is open for questions.
Recently, I saw some online posts. I have not verified it myself, but there is some claim that Fibonacci, in his introduction to his work, actually claims that this is an Indian technique.
Okay.
The summation
Okay.
of previous two numbers.
Okay.
I need to
Good.
verify it. Yeah,
Okay.
but I've
Good.
seen this,
See, there were some information flow from India to them, but I do not know. This is new for me.
They have in
Whatever
fact
you
shared
say.
the screenshot of the
Okay.
introduction to his work, and they claim that he says that. I
Okay,
have not verified
fine.
it myself, but
Okay.
just wanted to share it.
Okay, thank you.
No, no. What is well known is the decimal place value system going to Europe. Fibonacci's book was one of the
Okay.
most important sources for that. There
I
could
see.
have been
Okay.
other sources.
Okay.
So,
Okay.
in that
Okay.
decimal place value system into Europe.
Okay.
Fibonacci.
Yes.
During the talk, I had a question about your comment about Shunya, about being a placeholder versus 0. Just what is your thoughts? Can you tell us?
Well, here he is using it as placeholder only. Yeah. No, not the placeholder as in the case of decimal number system. It's just some marker which he is using, shunya and 2 to indicate that I have to multiply it by 2, and shunya to indicate that 2 to indicate that I have to multiply by itself, and shunya to indicate that I have to multiply by 2. That's it.
Similar to the Babylonian, the triad, like what they call it, the ratios. The Babylonian also there was some kind of.
No, I am not aware of it. Sorry. Yes.
Because all these mathematics actually used, because these are all, even now they are relevant.
Hmm.
In those days, what is the requirement for these mathematics? What did they actually cover? Did they use it for the architecture that they have?
So can I pass this to any of you if you are aware of it? Because I have not worked on mathematics per se except this particular thing.
Still they apply this mathematics.
Yeah.
They have applied it in prosody right here.
No, other than that, any other he is saying.
No, combinatorics is a very major thing. It occurs in architecture, music, in perfumery. So this is the original sort of summary of all mathematical techniques that can come in combinatorics. So this was widely used later in music prosody, but it was used by mathematicians also. This 2 to the power n was used in mathematics texts to write down the summation of a geometric series. And when this is used in Leelavati, later on when 19th century people translated it, they could not understand what is happening. Geometric series usually multiply same number n times, but he is using a technique which is a log n steps and not n multiplication.
Yeah.
So Colebrook couldn't understand what was going on. Just one small remark.
Yes.
This Vasu is used for 8. This system is called Bhuta Sankhya. That for numbers, you associate various objects. I for 2, Vedas for 4, etc. So in Pingala's Chandas-śāstra itself, there are about 5-6 such Bhuta Sankhya's here are used. So the Bhuta Sankhya system really goes back to earlier than 300 BC or what. I mean, otherwise it is in what is called Pancha Siddhantika Varahamira. So, I mean, you have to talk about numbers in a verse. Then you don't say 1, 2, 3, 4 and all that verse will become messy.
Yeah.
So you use this Bhuta Sankhya, but Pingala is the earliest use of Bhuta Sankhya.
Okay. Thank you, sir.
I have 2 questions. One is, I should say, a silly question. Why is a work on Chandas not written using Chandas? It's written in a sutra form. Okay. And the other question is, how well is all this duly recorded in books on history of mathematics, the Indian contribution?
Well, the second question is easy to answer. It is very well recorded. There are several books which mention about the contribution of Pingala. Of course, very late we came to know about it. I think when computers were discovered, at that time we didn't know that in Pingala Chandas-śāstra you have these formulae. But later on, I think Newton was one. 1981. 91 or 93, yeah. So during that time, it came to light. So this is something, so I should say,
Donald Knuth you have to mention.
yeah, Donald Knuth is there, yes, yeah.
Computer science is recognized by 1970s.
Yeah.
History of mathematics is even now not there.
Yeah.
Books on history of mathematics do not contain this. But some articles have appeared on binary numbers and prosody.
Knuth is also 1981 and Newton is 1993. So around 1980s, the computer scientists came to know about it. So if had Indians knew about it, the Indian computer scientists knew about this during the evolution of computers and all that, maybe there was total gap between the Sanskrit scholars and the modern scientists. If that were not there, maybe if we look at Panini's contribution as well as Pingala's contribution, both are very much related to the information technology. But somehow there had been a gap because of several reasons. I don't want to go into those details. There was a gap between the Sanskrit scholars and the...
You did not learn Sanskrit, you learned only English.
Yes.
All other countries learn sciences in their own language.
Okay, fine, fine.
If we had learned even,
Okay, right,
even
right.
in Kannada or Telugu,
Fine, fine.
there are works on proceeding in
Sure,
Kannada
sure,
and Telugu,
sure.
which would have
Yeah.
taught you all this
Then-
Dastara.
Sure.
So it is just
okay.
one reason.
Fine, fine, okay. That makes the thing simple. I agree with you. And regarding your first question, well, maybe if we look at the Pingala and Panini, they say Pingala and Panini were brothers, and of course this conclusion also they have come up with based on the two texts, the similarity between two texts and so on. So really speaking, there is no answer why he didn't write it in the form of chandas, why he wrote it in the form of sutras. Maybe because he is writing something which is succinct, and to have it in succinct form, you don't have to, you will not have to use any unnecessary words and all this. For that purpose, he had to resort to the sutras, not the chandas. If it is chandas, then he will have to think of some other words in place of these, and unnecessary words like cha, etc., which do not have any information. Such words you will have to use. So maybe because of that, or maybe influence of Panini, if he was contemporary.
I have a question here.
Yes. Yes. Yeah.
No, I think it's just not brevity.
Huh.
In the sutra style, you teach rules.
Yes.
And so in some sense,
Huh.
it's a systematic way of teaching algorithms. Panini is also teaching whole lot of algorithms to generate words.
No, but if you look at Kedarnath, he is also
No,
giving
words is a
algorithms.
way to remember.
Huh.
Sutra is a way to
Remember,
very
yeah,
concisely
Right, right.
teach all the algorithms, because you have all the meta rules, rule ordering. So you are really teaching the method of sequential computation by teaching something in sutra style. In the vritta style, that's an easy way to remember, but people used to memorize the sutras also.
Yeah.
So,
So
it's
maybe
it's
because-
not, it is nothing to do with brevity.
Or-
In that you will finally achieve brevity also.
Or maybe that particular period was a sutra period and people were,
Yes, yes.
that
But
might also
algorithms
be.
are best taught in a sequential
Right,
set
right.
of rules.
Yeah. Okay.
So I missed the first part of the presentation, so I don't know whether it has been discussed or not. I'm working on recursion in, let's say, sentential constructions. For example, relative clause construction, when you can stack sentences, and we are trying to understand what could be a beautiful model, thinking about the application in computer science. So I'm just wondering the kind of work that you're suggesting here, if it can be extended to a prosaic representation. Let's say John knows that, Mary believes that, Peter feels that. So that kind of a recursive construction when you're trying to account for it in syntactic structure. That's the first question. Second question would be, how would a model like, let's say, a connectionist model of language, do you think this kind of an analysis can be extended to find out the complexity of recursion sort of can be accounted for it? So these are the two questions. Sentential recursion. Yeah.
Okay. Okay. So the sentential recursion, as you have mentioned, the belief. So basically, it is the possible words, and they are embedded one inside the other. Okay. What I was talking about regarding Pingala has to do with the mathematical part. There the language was not involved. Okay. Whereas here you are talking about the language, semantics is coming into picture. And when the semantics is coming into picture, now how to model these possible words and the recursion or the embeddings in between, that's a totally different kind of thing, because we still do not know how to model the semantics. There are various approaches for knowledge representation. one approach in Indian theories is the Nyaya model of knowledge representation. But then in Indian languages we do not have this kind of recursion. Of course, we can have it in the sense of possible words, but one
we have constructions like mujhe ye pata hai ki wo janta hai ki so
okay, fine. So now coming back to this modeling of these things, let me fine. So let me come to the language part of it. If we analyze various structures that are embedded in the commentaries or the for example texts like Bana's Kadambari, you have no compounds are, but that is a different kind of thing. In compounds, well, I will come to the compounds in a moment. Various texts in Indian literature, they have specific structures. So for example, if we take the commentary, for example the Mahabhashya, Patanjali's commentary on Panini, this commentary has a well defined structure, and by well defined structure I mean, given a sutra, he is commenting on the sutra. So first he comments on what each word means, what is the importance of each of these words. If I remove one of the words, what will be the effect? Is anything missing in this? And then he goes on explaining what is the prayojana of this sutra and so on. So this is the discourse structure that is there. Now whether there is a recursion in this or not, what we have observed is, as far as the Mahabhashya is concerned, we can represent it as a finite state automaton. Okay. So some part of recursion might be there. Okay. For example, there is a prashna, then samadhana, and then there is an akshepa. So again it is a prashna and there is samadhana and so on till the issue is resolved. This is one kind of thing where small recursion will be there, not infinite. Then you have stories like Panchatantra, where you have story within story within story. This is a kind of recursion again. Okay. And here what happens is, from linguistic point of view, the pronoun, how to resolve the anaphora. So whether to go to the previous story and resolve it or back to the upper level and so on, it all depends on the context. Similarly, if you look at Kadambari, there you have the story of 3 generations, and they are again embedded, and then what I mean to say is, each of these texts have a particular structure, and that structure can be determined. How to determine that structure? Again, then there are theories within Indian tradition. These are called the Sangatis, and you have the Sangatis developed by various traditions, various schools. So Naiyayikas have given Sangatis, Mimamsakas have given Sangatis, Vyakarnas have given Sangatis to deal with texts pertaining to their discipline. Okay. Of course, that recursion cannot be infinite, and even the recursion which you are saying is not infinite. Maybe 3 or 4 levels you can go down. Now there is one recursion that is there in Panini's Ashtadhyayi itself. That recursion pertains to the word formation. In the word formation, he uses 2 sutras. One is Arthavat Adhatu Apratyaya Pratipadikam and Krut Tadhita Samasascha. So what is a Pratipadika or a stem? Anything which is meaningful, which is not a root, which is not a suffix, is a stem, nominal stem. And a Krudanta, that is a non-finite verbal form, nominal form, is also a Pratipadika. Okay? Or Tadhita is also a Pratipadika. And then from these Pratipadikas again you can get new Pratipadikas, because Tadhita is formed from a noun adding some suffix. So there is a recursion involved there also. And in compounds, as you have said, there is what he says is two words can be joined together, supa, a very simple sutra, but then he does not say that only two can be added. After adding two, you get one compound, you add another one, you get another compound, and so on. So there is a recursion involved there also. Yeah.
When is recursion preferred? When is iterative method preferred?
Well,
You have both the kinds of algorithms.
yeah,
now.
yeah. Now, when it's preferred means, okay. See, this I see only from pedagogy point of view. That's it. See, sometimes it is very difficult for a person to understand the recursion. But if you are thinking over it, the best solution that you get is the recursion. But when you are explaining it to others, you may find it difficult. Of course, there are certain problems such as Tower of Hanoi. You cannot explain it with iteration. Only recursion is needed there.
So, in general, recursion is the preferable thing.
I prefer recursion because you understand the beauty of it. Okay.
My question is to you, Professor Srinivas. Why did they come up with this Bhuta Aksharas and not just the number? I mean, why not just 1, 2, 3? You know,
No, you have to discuss mathematics in poetry, because it's verses which could be remembered. So within poetry,
Yes.
to introduce a word like 3423 will be very unpoetic. That's all. So they had the Katapayadi system, they had the Bhuta Sankhya system.
Hello. For finding the possible combinations of chandas, we use NCR, right? Instead, can't we use NPR and permutations?
No, just a minute. To find the
I understood it as
the prastara. Actually, prastara is you get 2 raised to n possible combinations given n syllables.
But,
so there is no NCR involved. NCR will be involved if you want to know how many combinations are there of one laghu. How many permutations, let me say.
okay.
So, give one laghu in a 3-syllable chanda, how many such possibilities are there? So, one laghu can be in the first place or in the second or in the third. So, 3C1.
Okay. Okay. Thank you.
Yes.
The standard combinatorial form Cn plus 1 r plus 1 is equal to Cnr plus Cnr plus 1 was known from Pingala times. Is there any reference to that?
Yes. Yeah.
Sir?
This one. Or yeah, I should go this way. See, how do you get this 2? By adding 1 and 1. How do you get 3? By adding 1 and 2. So this is the formula which you are telling about. Okay. Thank you very much.
Thank you, madam. Thank you, madam. Thank you for the wonderful lecture. Now I request Professor Srikanth Vedantam to hand over a food bag to Professor Amba Kulkarni as a token of appreciation and gratitude. Thank you, sir. Now I request Professor Devendra Jalihal to give the vote of thanks.
It was really a delightful talk, and the audience was amazing, very scholarly. I didn't know what to expect when I entered the hall. Just the title was Combinatorics in Chandas, and even before the talk began, I saw slides prepared by Beamer. So I knew this is going to be, not an ordinary humanities. Sorry, I apologize if I offended the humanities. It's going to be something on really computer science kind of a course, and so it continued. And of course, Professor Kannan didn't emphasize the mathematics background of it, but it was very clear. So thank you, Professor Kulkarni, for coming and accepting to visit IIT Madras and give this talk. And I would thank all the wonderful audience, Professor M.D. Srinivas and others who came and added luster to the talk today, plus the Humanities Department for agreeing to host and give this hall for the talk, and all the audience who came on Saturday morning, when so many things are going on in the campus. So thank you everyone for coming for this morning talk.